Hello, I'm Samarth Brahmbhatt presenting our work on zero-shot transfer of haptics-based object insertion policies. This is a collaboration with Ankur Deka, Andrew Spielberg, and Matthias Mueller. First, let's look at how we humans insert objects in constrained locations. We first estimate the target location visually and then guide our actions by comparing the contact forces or haptic feedback with our mental model to finish the task successfully. In this work, we learn a robot manipulation policy for a similarly contact-intensive task, inserting plates and cups into narrow slots. Assuming the object has already been grasped, we first move straight to the vicinity of the visually detected slot. We then execute the learned policy, which uses robot proprioception and end effector wrench as inputs. Our policy does not require to know the target pose or the object and environment geometry accurately. Various algorithms have been proposed for tasks like peg-in-hole insertion before. For example, some policies are hard-coded heuristic, some require unoccluded visual observations of the contact interaction. Imitation learning policies require expert demonstrations. Some policies require pre-training or fine-tuning in the target environment, and some require special fingertip sensors. To the best of our knowledge, ours is the first non-heuristic insertion policy that is trained completely in simulation without pre-training or fine-tuning with real-world data or expert demonstrations. How do we do this? Here you see a visualization of our simulation environment. At every step of the episode, the policy pi uses an edge step stacked history of proprioception and contact wrench observations to predict A, an action that denotes the desired sixth-off motion of the end effector during the next step. Internally, an action moving to the observed target in a straight line is added to the action predicted by the learned policy to derive the final action. The policy loop shown in blue runs at 20 Hz and the action at each policy step is executed on the robot by a 1 kHz operational space control loop shown in orange here. We use reinforcement learning to train the policy. The reward function contains a constant time penalty, a penalty proportional to the distance from the target, a large penalty if the plate is dropped, and a large reward for success. We use the soft actor critic algorithm implemented in TensorFlow agents with a group of 20 parallel experience collection workers. And here are some simulation executions of the learned policy. We perform our experiments on a Franca Amica Panda robot, where 1 out of 6 slots is selected as the target slot, and a camera at roughly the shoulder position is used to estimate the slot position before the episode starts. To test the ability of our policy to succeed in spite of unexpected collisions, we also place a blocking object, like the cup or the phone charger shown here, in the target slot. Several measures during simulation training are necessary to enable this policy to perform successfully on the real robot. Firstly, we add to the real target pose at each step a sixth-off noise sampled once at the start of the episode to get the observed target pose. This reflects real-world conditions in which the target pose detected by a vision system is not completely accurate. It also prevents the policy from overfitting to the training environment geometries, thus allowing it to generalize to different objects and slot shapes. This and all the following bar graphs compare success rates calculated over 4 trials per slot for 6 different slots. Blue bars show real robot evaluations, and green bars show simulation evaluations under noisy real-world-like conditions. Training with per episode noise in the observed target pose is crucial for sim to real transfer. Without it, the policy has 0 success rate on the real robot. A proper observation memory is also important. Our algorithm, which uses 8 steps of stacked observations, outperforms 16 steps of stacking, no stacking, and recurrent memory, and also has the smallest sim to real gap. Policy execution on the real robot is implemented with a client-server architecture. The high-frequency operational space control loop keeps the robot moving during policy inference and also during the round-trip communication of the observation and the action. However, this is not modeled in most simulators, and simulation time just stops during policy inference. We found that modeling this policy inference and communication delay during training is also quite important for sim to real transfer. And our policy shown on the top left outperforms heuristic and learned baselines in terms of real robot success rate and sim to real gap. By making a minor modification, which is adding a height offset to the pose observation given to the policy, our policy can also generalize to a variety of plates of different sizes and weights, and also a cup, which has significantly different geometry. As shown by the various clusters here, our policy consistently outperforms other baselines across different objects. Here, you can see our policy being executed for inserting different plates and a cup. Here, we show the same policy inserting a cup and after that a plate. Because both episodes are given the same target slot pose, the policy inserts the plate in the next free slot. Thank you. The code and the trained models are available at this website. We look forward to interacting with you at the poster.